All right, into chapter 9, our very last chapter. That's kind of exciting. This is section 9.1, Introduction to Vectors and Vector Addition. So we have two definitions. The first is a scalar. A scalar is a quantity that has magnitude only, so only a number. Where a vector is a quantity that contains both magnitude and direction. So let me give you the most common example. Speed versus velocity. Many people interchange those two things. They're related, but they're not interchangeable. They're not the same. Speed would be, I tell you I'm driving my car 50 miles an hour. That's a quantity. It has a magnitude, 50 miles an hour, but that's it. Where velocity would be, I tell you I'm driving my car 50 miles an hour due north. So the big difference is there's a direction. So that's what makes something a vector, and that's what makes velocity. Velocity not only has to have the speed, it also has to have the direction. So vectors are very commonly represented with an arrow, and the length of the arrow represents the magnitude, and the direction is given by the angle. So for example, here's a vector. We might have a vector something is pushing with 40 pounds of force at an angle of negative 38 degrees. So that's a vector. It's got a length, 40 pounds, that's a force, and then it's got an angle, 38 degrees. Oh, here's another one, velocity. So we are going 255 miles per hour, perhaps we're in an airplane, and we are going 17.4 degrees south of due west. So again, we've got a speed and an angle. That's a vector, that's velocity. Last one, something moved 22.8 miles, and it moved in the direction of 51.2 degrees north of due west. So again, notice I'm giving you a number, 22.8 miles, and then I'm telling you the direction. Often there is more than one vector acting on a body, and we want to know the combined results. To do that, we add the vectors. There are two different techniques for visualizing the addition of vectors. So the first is called the tail to head method. So you draw the first vector, here's vector A, and then where this vector ends, at its head, you put the tail of vector B. And then the result, R, is called resultant vector, is A plus B. So A plus B would be R. The other way to do it is called the parallelogram method, where you place both vectors starting at the same spot, and then you draw the parallelogram that forms. Now, I'm not a big fan of this parallelogram method because, I mean, if I'm drawing this thing, what I'm really doing is taking B and putting it up here anyway. This is really vector B. I'm really just using the first method, the tail to head method. So either method can be used. Some people find it easier to visualize it this way. It doesn't work so much for me. If you have more than two vectors, however, you have to use this method where you would have one, and then the other, and then the third one, and then your resultant would go across. When a vector is multiplied by numbers, the direction remains the same, but the magnitude is multiplied by that same number. So for example, the vector 3a goes in the same direction as vector a, but it's 3 times as long. Of course, if you multiply by a negative number, multiplying by a negative number does reverse the direction. So if this is vector a, then the vector negative a would have the exact same length, but would go the opposite direction. All right, and subtracting vectors a minus b is the same as doing a plus negative b. So a plus b, but in the opposite direction. All right, let's look at a few examples here. So we have vector a, vector b, and vector c. And we're going to add a plus b. So to add a plus b, I would draw vector a, and things here are not particularly exact. You can see I'm approximating. That's not bad though, same direction, same length. And then to add b, I would start here, draw vector b, like so, and so this would be a plus b. And again, it's usually called R for resultant vector. B plus C. I would draw B. And that might be a little too long, but you get the idea. And then vector C goes this way, like so. So this vector here, starting where B began, would be B plus C. All right, A minus C. Here's vector A. Now minus C means keep the same length, but go in the other direction. So now it's going to go from left to right. So this is A. And there's minus C. So this resultant vector would be A minus C. Oh, you know, I should be, sorry about this, that notice these are all written in bold. When you type vectors, quite often we indicate vectors by typing them in bold. When we write them by hand, we put little vector symbols over the top of them. So I should have put little vector symbols over the top of all my vectors here. So I'm just going to go back and do that now, to represent that they are vectors, not just numbers. Numbers we don't bold, vectors we bold. All right, A plus B plus C. So A goes about like this. And then B is about like so. And then C goes this way. So notice we're going to cross back over A. That's okay. There's vector C. So A plus B plus C would be that tiny little vector right there. That's A plus B plus C. All right, 3B. 3B means take vector B and make it 3 times as long. So 3B would look about like this. And then vector C is the same. That's about like that. So here is the vector 3B plus C. Now, in the very near future, in the next couple of sections, we're going to learn a way to actually add 2 vectors. So we'll do more than just having pictures here. If I give you the length of this vector, and I give you the angle of this vector, and I give you vector B, and I give you its angle, we will actually learn techniques for exactly adding them and getting the answer. Today, we're just doing approximations. All right, last one on this page. Here's vector A. Then we need minus 2b. So minus 2b is going to mean we're going to go in that direction, but be twice as long. So that's going to go up this way, roughly. 2b, looks like so. And then subtracting c, remember what c looks like. So now we're just going to go the opposite direction. Start here and go c. So here's vector c. So this would be our resultant vector, which is a minus 2b minus c. Vector. Big long vector. All right, the last thing we have in this section, this is a nice short one, as you have probably gathered, is 2 vectors at right angles. 2 vectors at right angles with one horizontal and one vertical can be added by using the Pythagorean theorem and the tangent function. So, find the magnitude and direction of the resultant vector below. So A is 318 pounds, and B is 285 pounds. So notice what we have here. This is really side B over here still. 285 pounds. So to find the resultant vector, I can use the Pythagorean theorem. R squared is a squared plus b squared. Grabbing my calculator, that's 318 squared plus 285 squared. And then I'm going to take the square root of that answer, and I'm going to call it 427. So these two things together are pushing with a force of 427 pounds. And now we're going to figure out this angle, theta. Notice that tangent of theta would be b over a, opposite over adjacent. 285 over 318. So theta is, I gotta check. I suspect I'm in, I am in degrees mode. I was betting I was in radians mode, but I am in degrees, so that's good. So I'm going to do tangent inverse of 285 over 318, and we're going to call that 41.9 degrees. Okay, so if two forces are acting at right angles, and one is horizontal and one is vertical, then we can exactly add them. I can tell you exactly how long the resultant is, and I can tell you exactly the angle at which this object would be moving based on that force and that force. Like I say, we will learn more about this in the very near future. How do we actually add any two vectors? They won't have to be two vectors at right angles.